students, welcome to All Things Pharmacy. Today we're going to be discussing the 10 reasons for optimization, reasons why you should optimize a lead molecule. First, we're going to start by describing what optimization is. Optimization is the act of making something fully perfect, fully functional, or as fully effective as possible. And for you to do this, it requires you to change that thing. So in this case, we're talking about a lead molecule. So that means that for you to make a lead molecule as fully effective as possible, it requires change. This change can be done through modification, through rearrangement, and through manipulation. So in this case, we're changing the lead molecule to achieve the best pharmacological properties and the best physiochemical properties for its therapeutic use and its storage. The first reason for optimizing lead molecule is to improve selectivity and safety. Safety in terms of the therapeutic index. Therapeutic index is the ratio at which compares the concentration at which drug is effective and concentration at which drug is toxic. If there's a large difference between these two concentrations, that means that the drug has a large therapeutic index, which means that it is safe. It is more safe to use than a drug which has a smaller therapeutic index. A smaller therapeutic index is when there is less of a difference between the concentration at which drug is toxic and concentration at which drug is effective. You'd also want to improve selectivity, which simply means that making the drug more selective towards its target tissue or target organ or target site. Actually, I think we should go with target site. And if a non-selective drug is most likely to bind to a lot of different target sites, and when it's selective, there's going to be that one particular target site it will bind to, which makes it able to achieve a specific therapeutic outcome, which is what is needed for the patient. Another reason why you want to optimize the lead molecule is to improve the oral absorption of the molecule, which means to make it more easily absorbed in the gastrointestinal fluids. This may be because the target site may be in the area of the GIT or somewhere along that area, and so it's important that it should be able to be orally absorbed. Now we're going to look at an example. For example, norethindrone and progesterone. These are contraceptives and they are hormones. Norethindrone is absorbed orally and progesterone is not absorbed orally. Another reason why you'd want to optimize the lead molecule is to decrease the likelihood of the drug crossing the blood-brain barrier. When a drug can easily cross this barrier and reach the brain, it is likely to cause toxicity to the brain and also have adverse reactions, and this is not good for a patient. There's also no need for a drug to cross this barrier if it's meant to have a therapeutic effect somewhere else in the body. Now we're going to move on to the next reason, which is to improve the onset of action or effect, to have quick onset of activity, which may be necessary in emergency situations, life or death type of situations, where you need to have an immediate therapeutic effect to potentially save a patient's life, and a quick onset is very, very important. As an example, we're going to look at the structure of pentobarbital and thiopental. So thiopental has a quick onset of action, and this is because of the sulfur atom that is attached to the molecule. As you can see that there is no sulfur attached in the pentobarbital. Another reason of optimizing a lead molecule is to improve or increase the duration of action. Increasing the duration of action means that the drug gets to stay in the body for a longer time, which means that it gets more time to exert its therapeutic effect. And now, as an example, we're going to look at procaine and procanamide, and with regards to their stability to hydrolysis. Procaine has an ester group which makes it readily hydrolyzable, which means that it breaks down during a process of hydrolysis, which involves water. So when it's in close contact with water, this procainamide breaks down. And procainamide, instead of having an ester bond, it has an amide bond, and therefore it's less likely to break down due to hydrolysis. This means that procainamide is more stable than procaine. This is also good for storage purposes. It also improves the storage stability of the drug if it's less hydrolyzable. The more stable it is, the longer the duration of action. Another reason for optimizing a lead molecule is to improve the drug tissue distribution, and increasing this can lead to a decreased duration of action, particularly for drugs that are excreted unchanged, meaning they are excreted in the same form structurally as they were when they were taken into the body. The decreased duration of action is good for drugs that are toxic, because if there's a decreased duration of action, it means that the drug spends less time in the body, which means that there's less time for it to have a toxic effect or for it to show any adverse effect. Increasing the drug tissue distribution also means that there is more of the amount of drug that reaches the target site, the target tissue or target organ. Now, as an example, we're going to go back to the barbitals. Now we're going to look at phenobarbital and thiopental. Phenobarbital has a long duration of action, but thiopental has an increased tissue distribution because of the sulfur atom, which makes thiopental more lipid soluble, and the phenobarbital does not have the sulfur atom. Another reason for optimizing lead molecules is to control the rate of elimination and or metabolism. By controlling the rate of elimination and metabolism, you're also controlling the duration which the drug gets to stay in the body, the amount of time which the drug gets to stay in the body. And for an example, we're going to look at procaine and procainamide. Like we said, procaine has an ester bond and procainamide has an amine bond. By changing the ester to the amide bond, you are also changing the rate of metabolism, because these lead molecules, they are broken down or metabolized in the body through hydrolysis, and by changing to the ester to amide, you are delaying the process of hydrolysis and hence controlling the rate of elimination or the rate of metabolism, which means that procainamide is going to take a longer time to be metabolized as compared to procaine. I also just wanted to mention that procaine and procainamide undergo enzymatic hydrolysis, not just hydrolysis on its own, but it involves enzymes. The enzymes facilitate the breaking down of bonds in the molecules with the addition of water. So it's not just water on its own, but it's also enzymes. The enzymes also play a role in the breaking down of procaine and procainamide. Another reason to optimize lead molecules is to control effects of enzymatic activity. If you control these effects, you can in turn improve stability of the molecule. And for this, we're going to look at an example of penicillins. These penicillin G and penicillin V, these are natural penicillins. Another name for penicillin G is benzyl penicillin, and another name for penicillin V is phenoxymethylpenicillin. These penicillin molecules can be broken down by an enzyme called penicillinase, and or another name for it is beta-lactamase. And this enzyme particularly targets the beta-lactam ring that is found in these penicillins, and this ends up breaking down the molecule. Once the penicillinase attacks and breaks down the beta-lactam ring, that means that the penicillin no longer has a therapeutic effect. Both penicillin G and penicillin V are not stable to the enzyme. However, penicillin G is less stable as compared to penicillin V. There is also methicillin, which is a semi-synthetic penicillin. Penicillins were optimized to make semi-synthetic penicillin. So methicillin is more stable to this penicillinase enzyme, and it's more stable because it has a bulky hydrocarbon chain which acts as a shield. So this optimization is more of a steric one, where it just changes the effects of the structure, and this bulky hydrocarbon chain shields the penicillinase from the beta-lactam ring, and therefore it doesn't attack the beta-lactam ring. However, it's also important that this hydrocarbon chain is not too bulky, because if it's too bulky, then it will prevent the penicillin from actually binding to the target enzyme that it's supposed to bind to be therapeutically effective. Another reason for optimizing a lead molecule is to reduce the cost, and this is especially a good thing for patients because some patients cannot afford certain medications, and it's always a good idea to make medications cheaper for the patients so that they can be more affordable, especially if these medications have the same therapeutic use or effect. And so an example of two molecules that do have same therapeutic use but one is cheaper than the other is beta estradiol and diethyl stilboestrol. Diethyl stilboestrol is the cheaper product. Now we've come to the last reason for optimizing lead molecules, and this is to provide marketable alternatives. Patients respond to medication differently. We as people will respond to the same medication differently. Medication may work for one patient and not necessarily for the other patient. This is why it's good for us to have alternatives. And an example is chloroquine and hydroxychloroquine. These both have the same therapeutic effect, but they have a little difference in their structures, and they are used to treat malaria. They're part of the 4-aminoquinoline family. Thank you for watching this video. Please don't forget to like, share, and comment any questions you may have, and subscribe. Until next time.